In this video, we shall look at a couple of challenging problems on simple harmonic motion. Problem 1. A block is on a horizontal surface of a shake table that is moving back and forth horizontally with a simple harmonic motion with frequency 2 Hz. The coefficient of static friction between the block and the surface is 0.4. Find the maximum amplitude of the simple harmonic motion so that the block does not slip along the surface. So what we have is you have a surface, say of a table, on which you have this block resting, like that. And this table can move back and forth horizontally, like that. So it is a shake table of some kind. So the amplitude for this oscillatory motion is A, let's assume, measured in that manner. Of course, we want to determine the maximum amplitude, the maximum value for A, so that the block does not slip along the surface. So there is static friction between the surface of the block and the surface of the table. And that static friction plays an important role in keeping the block in place when the table shakes back and forth. The maximum value of that static friction is characterized by that coefficient of static friction. So given the coefficient of static friction is 0.4, what is the maximum amplitude of that simple harmonic motion so that the block does not slip along that surface? So let's look quickly at the free body diagram. Let's suppose at one moment the table is moving like that with a block on top. So that means there must be static friction acting in that direction. Of course, there is the weight of this block, let's call it mg, and there is this normal force acting upward, and let's call it capital N. The acceleration is therefore in that direction. So from the free body diagram, we know that the net force acting on that block at that point is given by mass times acceleration, which in this case, the net force is provided by only the static friction, and let's call it F sub s. Maximum amplitude corresponds to maximum static friction. And that we know, it's given by the coefficient of static friction times the normal force. So equating ma to mu sub s, normal force is the same as the mass times gravitational acceleration, namely the weight. You see the mass goes away, and we get that equation. We also know for simple harmonic motion, acceleration is coordinate dependent. It's given by minus angular frequency squared times that coordinate or the position. So the magnitude of the acceleration is omega squared times the position measured from the equilibrium position. At amplitude, this acceleration is just omega squared times amplitude. We are given frequency in the units of hertz, that is just f. And 2 pi f is omega. Frequency in hertz is related to frequency in radian per second by that equation. So substituting all the information that we have thus far, omega squared is 4 pi squared f squared, that's that, times the amplitude equals mu sub s times gravitational acceleration, that is that term. F is given to be 2 Hertz, so 2 squared, that is 4, times the amplitude, which is what we want to find. Mu sub s is 0.4 times gravity 9.81, and you see you can determine the maximum amplitude, which is 0.025 meter, or simply 2.5 cm, and that solves the problem. Problem 2. A uniform rod of length 2 meters oscillates about the pivot point O, so that is the pivot point. Find the value of x, the distance between the pivot point and the center of mass. So that is that distance x there, which gives the least period for the oscillation. And what is that least period? The center of mass is marked with that red dot. So what we have is a physical pendulum pivoted about that point. This physical pendulum is in a form of a uniform rod. So we know the period for the oscillation of a physical pendulum, such as this one, is given by 2 pi square root the moment of inertia about that pivot point over mass of the pendulum times gravitational acceleration 9.81 times that distance x, which is the distance between the pivot point and the center of mass. The direction of oscillation is given by these arrows. So step number 1 is to determine the moment of inertia of this physical pendulum about that pivot point. And we can do that by using the parallel axis theorem. Parallel axis theorem says the moment of inertia for such a body is given by the moment of inertia about an axis through the center of mass of the body, meaning an axis passing through that point, plus a term, which is the mass of the body times the square of the distance between the center of mass and the pivot point, or the new axis of rotation, in this case, x squared. The moment of inertia of such a uniform rod about an axis passing through the center of mass is given by 1/12 times the mass of the uniform rod times the square of the length. And to that we add the term mx squared to get the moment of inertia about that point, or about an axis passing through that point. Substituting this in here, we get the complete expression for the period of oscillation for such a pendulum. So I is 1/12 ml squared plus mx squared over the mass of the uniform rod times g times x. And you see the mass cancels out, giving you an expression for the period of oscillation in the following form: 1/12 L squared plus x squared over gx square root. So let's write the expression on top, and we can rewrite that expression in the following manner, taking out that constant term out of that square root sign and write it in that manner. Now we are ready to solve the problem. We want to find the value of x, which gives the minimum period for the oscillation. So the value of x that makes capital T minimum. So all you have to do is to determine dt dx. Let's take the constant term out. Now let's differentiate the square root term. It will be half L squared over 12x plus x to the power minus half. Now you differentiate the term under the radical sign. So in this case, L squared over 12, when you differentiate 1 over x, you get minus 1 over x squared, plus differentiating x with respect to x, you get 1. And that's the total derivative. Setting dt dx to 0, meaning we can set this term to 0. So that means you have L squared over 12x squared equals to 1. And you can solve for x. That makes dt dx 0. And it will be L over square root 12. Since L is 2 meters, so x that makes t minimum is 2 over square root 12 seconds. And that's going to give you 0.58 meter. And that's the answer for part A. So the answer is written here. Now let's do part B. Now remember the period expression that we have derived a few minutes ago. It's given by 2 pi over square root g times the square root of L squared over 12x plus x. So to determine that least period, all we have to do is to substitute x inside that expression, and we will get that least period. And when you do that, you have 2 pi over square root g square root. L is 2 meters, so 2 squared over 12 times 0.58 plus 0.58. And that's going to give you an answer of 2.16 seconds. And that solves the problem. As always, thank you for watching.